prices kind of over data points, which that doesn't really make a lot of sense. You can right-click histogram, and now you kind of see all the prices in Ames, Iowa for houses between 2006 and 2010. Right, pretty cool, pretty cool. Yeah.
That column is called sales price, right? Or was it called target?
So it's called target. It is the sale price. Does that make sense? So the target is in machine learning. That's the value that we're trying to get. Right. So the number of rooms drives the price. The price doesn't drive the number of rooms. If that makes sense. So data is equal to Ames data. I'm just going to bring that in as a panda for right now. I'm going to go year. I'm just going to go capital Y, R, SOLD, capital S is equal to data, the string capital Y, capital SOLD, year sold, dot values. And that just extracts a column from the vector from the data set as year sold. And now I'm in an array of 64-bit floating numbers. So I'm going to copy that. We're going to do it 4 or 5 more times. You can go through the data set, or maybe the Ames feature names, and you can kind of pull out the feature names you want. I've got a few here that I'm going to type in because I've kind of played around with this and I have some idea of what I want to do. Actually, I'm just going to go ahead and grab 2 of them. For now, we're going to grab that, and we're going to grab capital G, R, capital L-I-V, capital A-R-E-A. And that's ground level or above ground living area. And then you can look at kind of the average house in Ames, Iowa is like 1,400 square feet or something. And then there's the year sold here. So let's see if we can see the Great Financial Recession. Histogram, 2008. Yeah, I mean, there's a few less houses in 2008. 2009 had a lot sold. And then actually 2010 didn't have a lot sold. But this was kind of the start of the recession, although this was technically kind of the bottom of some of the economic signatures. It took about 2 years to fully collapse. Okay, let's go ahead and plot some of this data. Let's go plt dot figure, plt dot plot. GRLIVAREA, comma, TARGT. And I'm going to make a marker size of that as an O because I actually just want data points. You know, that's too many data points. I'm going to make a period as my marker size. I like that plot better. Right? And so we can see, well, we can't see. Let's put some X labels in this. plt.x label. And that is above ground living area in units of square feet. And that's something that you can get from the description if you look through the data set more on your own. And then the Y label is going to be price. In USD. In 2008 US dollar, which is a lot more than 2024 US dollar, but well, this is a little hard to read, like 500,000. So let's go US, a 1,000 US dollar. And then I'm just going to divide the target here by 1,000. And that way you know that this is a $700,000 house. I have no idea who lived in a 4,400 square foot, $700,000 house in Ames, Iowa. None of my friends. Yeah. So if you're wondering where my house was, it was down here, somewhere around here. So on the bottom side, but definitely below 100. So, and then it kind of makes you wonder, right? A way to look at this plot is anything on the vertical line is going to be quality. So someone paid a lot of money for a small house here, and somebody paid $180,000 for something that had 6,000 square feet. So, I mean, it must have been a very large old home. So that is the Ames data set. I guess there's two quick things you can do. You can put a grid on it. And plt.tight layout. And that way your legends show up, and that is the Ames data set. All right, so next let's look at, let's say we want to predict the value let's say we want to predict the value of a house based on the amount of living area that we have. So to do that, we may want to do this. We can build everyone's friend a linear model, and let's say we call that price underscore model is equal to theta 1 plus theta 2 times the average living area. Right, so that model comprises two parameters, theta 1 and theta 2. Let's go ahead and just solve for those parameters or play around with the model that has those parameters. And then we will come back and look a bit at the map, right? So we're going to do this a little bit backwards, but that way we know what we're trying to get. So let's say model the price of a house. So if you weren't a little frustrated already, the typing things in like capital GR, capital LIV, capital area, that gets a little cumbersome, right? So let's just think about this in terms of our general machine learning models. We're just going to go capital X is equal to GRLIVAREA. And that's just going to redefine all of my data as X. And I just do that because in machine learning, that's very much the common way of doing that. Capital Y is equal to target, right? And now I have my machine learning data set, X and Y. Okay, and model underscore X is equal to np.linspace 0,5,000. That just is going to create a vector in the X domain that's 50 elements long from 0 to 5,000. And 5,000 is, I mean, there was 1 or 2 houses above 5,000 square feet, but we don't have any data to model out to this, right? So we're just going to, the model's going to consider it, but we're just going to plot out to about 5,000 square feet. That's all that's doing. All right. So now let's just build out that equation we just had. So we had theta underscore 1 is equal to, I don't know, what do you want to use? Just, we'll put 0 for now. We'll come back to it. Theta underscore 2 is equal to 1. Those are, actually, we'll just do 1 and 1. That sounds good. And then model underscore Y, capital Y, underscore manual is equal to theta underscore 1 plus theta underscore 2 times model underscore capital X. And now, yeah, that's right. I have created this wonderful model of something, right? So, but I guess we have to plot it in our data to have it make sense. So what I'm going to do is I'm just going to copy my figure from before. You can retype it, but there's no reason to copy my figure from before. And I am going to add a, real quick, I guess, let's do plot X, plot capital Y divided by 1,000, just so we know that we're plotting the right data, right? Okay, good, got the right data. And now let's go plt dot plot model underscore X, comma, model underscore Y underscore manual. I'm gonna give it a dashed line. That one right?
Yeah.
Yeah. I actually kind of saw that out of the corner of my eye before, but wasn't fast enough. Okay, how's that for a model? That the world's greatest. Would you like to use that model to buy a house price? Probably not. Depends if it's your money or if someone's buying your house. If someone's buying your house, that's a great model, right? So let's go ahead and think about what our theta 1, theta 2 values are, right? It's just y equals mx plus b. So theta 1 is our y-intercept. A house of 0 square feet could cost $0. I mean, there's land, there's other things, but that's not an obscene parameter to guess. So, or $1, I'll just leave it at 1. That's fine. And we just have to find a theta 2 value that that would work for this. So maybe it's got to be less. So 0.5 maybe. We'll cut it in half. That's a little closer, but not quite there. 0.15. Oh, that looks pretty good. A little high. 0.4. 0.3. All right, there's my model. And in this case, I am the machine that fits it. Our model is relatively easy. We only have we only have one theta, but then you always have to add a base theta. So we have two parameters that we're trying to solve for. And we'll talk through some of that math in a bit. But first, let's start with some code. Okay, the first issue we're going to have is if you come on down here and you go x dot shape, what you'll see is you have a shape of vector 1460 by nothing, which isn't how we do math, right? A vector is 10 by 1, 100 by 1. Does that make sense? Have you heard those terminologies? Have you ever heard of a vector is 100 by undefined? No. And so MATLAB doesn't do this. MATLAB says this is 1460 by 1. And it's beautiful for engineers. But for us, we are working in Python, which is a little bit more of a baseline programming language. And in computer science, you definitely don't have to have an expression there. But we need one, right? We need one because we're special and we want that extra dimension. So we're going to go x is equal. We're going to go x is equal to np dot expand underscore dimensions, comma, capital X, comma, AXIS is equal to 1 and hit F5. And now I'm going to come over here and hit up twice and hit X shape. And now I have X is equal to 1460 by 1. It just it allows us to do math. That's all it is. You know, kind of another line of code you wouldn't need in MATLAB. But Python does have its benefits also. I don't mean to like be super negative about it, but okay. I'm going to do the same thing for y, and now I have these two expressions. Oh, I have to do the same thing for model underscore x equals same thing. And now all of these x, y, model x. Okay, model x. Yeah, they're all 50 by 1, 1460 by 1, 1460 by 1. So we're all good. Let's do so let's compute the linear regression solution. Let's compute the closed form solution. So I'm going to go compute capital X underscore B is equal to NP dot ones. And we'll talk through a little bit more of this math in a bit, but I need to create a matrix of ones to use here. Now I could absolutely just type in the shape, the size of my matrix of ones, but I'm just, because I don't want to make a mistake, I'm going to go x dot shape 0, comma 2. And that should give me a matrix of ones that is 2 columns of 1 by however many data points I have in X, which is 1,460. Right? Because I have 1,460 home prices that I'm trying to model. Okay, so that is going to be my data set, or the start of my data set. Now, X underscore B for all of my rows for column 1. And again, the index starts at 0. So column 1 is actually my second one here, right? again, X is my data. So I need to get my data into X. And we'll talk a little bit later about why we have this bias term 1 here at the beginning. But I want to get all of my home value prices into X. So X of B for all of my columns for row 1, I'm going to reset those as X dot capital T, and that's a transpose. And now what I have is an X parameter for 1 and an X parameter for my price. Why do I have 2 columns? Anyone want to take a stab at that? Why do I need 2 columns? It's called a bias term. How many parameters do I have in my linear model? What was the equation? Theta 1 plus X times theta 2. I need something to multiply by theta 1, right? I had no data for theta 1. It's just my bias term. It's my Y offset. And so I just have to have a columns of 1 associated with my bias term. Does that make sense? Right? Because I only have 1 feature that I'm putting in. If I was putting in 2 features, size of the house, size of the swimming pool, I would actually need 3 columns because I need a bias term to account for my Y offset. We don't know what the Y offset is, right? We like the idea that a house of 0 square foot is $0. But if you go try to buy a house of 0, I have $0. Can someone sell me land that's associated with a house that has 0 square feet? No, like there's a bias to it. So that's what this first column is for. And I understand we haven't talked about that yet, but it's kind of a stair step of a little bit of problem solving, a little bit of math back and forth. Okay. Theta underscore closed underscore form is equal to theta. Wait, sorry. Is equal to np dot lin alg dot inverse, linear algebra inverse of that expression we wrote before, which is x underscore b. That's our x with our bias term. I need to take a transpose of that. Matrix multiply, which a way to do matrix multiply is just to use the at symbol of x underscore b. And now that's going to be my inverse. And now I need to multiply that by x underscore b, which was on the outside of my inverse, dot t. And then I had a last matrix multiply of y at the end. Okay, b underscore b is not defined. That's fine. And did I do it twice? I did it twice. There we go. Theta closed form gets me 2 parameters. It gets me 18,569 and 107.13. Those appear to be off. They might not be bad. That might be right. But let's go ahead and put those back into our model because we divided by 1,000 in our plotting. So this might actually be pretty close. What this is telling me is that for my bias, I have 18,500, which essentially says if you had a house with 0 square footage, it would cost you $18,500. Makes sense? That's about what an empty lot costs in the Midwest in 2008. I'll give you that one. 107. So before I had 0.14 or something that I kind of estimated, eyeballed to get this line, and so that's a lower slope. Yeah, maybe I estimated high. I kind of thought I estimated high. Once you see what the computer gets you, you're like, oh yeah, now I see it. Okay, so let's go ahead and plot that. I'm just gonna copy this code down again. plt.plot x underscore model theta closed form comma, do that marker. So what is, oh, model underscore X. Really point out that. Aha, it's always an issue. Okay. Oh yes, sorry. Theta, no, that's not what we want. So theta closed form just gives me my parameters, right? I need to actually solve that. So model underscore Y underscore close underscore form is equal to theta underscore close underscore form 0, because that's our first term, theta 1, plus theta underscore closed underscore form 1. Bring this down on the next line. Maybe it's like this. We'll just go to the end. Okay. Times model underscore X. That'll work. So this is gonna be model X, model Y closed form. And that should get me a solution. Oh, that's not quite what we want because we have to divide it by 1,000 just for our plotting. There we go. Right? I mean, that looks better than my closed form solution. I mean, than my estimated solution. We notice that a house has some sort of bias term, right? And it pretty much kind of cuts down the middle. And then you could say everyone below this line got a great deal. Everyone above the line got an awful deal. If all you're concerned about is above ground living square footage, right? If that's all you're concerned about, and nothing else matters, above the line, the bad deal, below the line, the great deal.